Right, so what do you guys want to go over? So, okay, so let's do 54 from the list of practice problems. So let's see, number 54. Okay, so this here is a good example of a quadric surface that you are supposed to I think it's a quadric surface from 12.6, I think that's the section. So graph and classified this quadric surface, label the vertices and the trace with x equals 3. So let's start off with this and then we can move on to others. So what I will do first is I will group the terms of 4x squared will be grouped with 16x, then minus 36y squared, minus 9z squared, and then all of this will equal to 20 because I'm moving the 20 over to the right hand side. Now that I group the variables accordingly, I can complete the squared. But before completing the squared, I would like to factor this 4 out. Otherwise, it wouldn't work. I have to factor that 4 out first. So it will look like this: 4 times x squared plus, and then 4x, and then minus 36 y squared minus 9z squared equals 20. So now I can complete the squared. In that blank space that I left here, I'll add, so I divide this by 2, that 4 divided by 2 is 2, 2 squared is 4, so I add 4 here, but in reality, I'm not adding 4 on the left-hand side, I'm adding 4 times 4, so that makes 16, so I'm adding 16 on the left-hand side of the equation, so that for that reason, I have to add 16 on the right side, like that, right? So what do we get? We get this, we get 4 in parentheses, x plus 2, all of that squared, minus 36y squared, minus 9z squared, equals to 36. We divide everything by 36, giving us, in parentheses, x plus 2 squared, divided by 9th, minus y squared divided by 1, then minus z squared divided by 4, equals 1. So what kind of quadric surface is this? What type is it? So how do we classify this?
Sheet.
Yeah, so this is a two-sheeted hyperboloid, correct? Hyperbola of 2 sheets, right? Or two-sheeted hyperboloid, two-sheet hyperboloid. And it gives it, what gives that away is the 2 negative signs that we have, right, on the terms on the left-hand side. So that's cleared, hopefully. There we go. Next, the two-sheeted hyperboloid, how does it look like? I'm okay for you to say something like this, like the 2 parabolas or paraboloids that are facing away from each other, something like this, right? But oriented in what, like in which direction is it oriented? Is going to be, yeah, in the x direction, right? Because this term here is the positive direction. So I'll try to make it clear that this will look like some. So let me see. I think I will start off with something like this towards the x axis, or in this direction, like this, and then I'll fix other details from that, and then I'll do the same thing on the other side. So something like this is clearly indicating that it's going somewhat in the x direction. Let me see, can I? Okay, I think that's fine. There you go.
There you go.
And
That's all.
all right, so let me do that. Okay. And the center for this, what is the center for that thing here? The center will be the point -2, 0, 0, right? Yeah, so -2, 0, 0. So I'm gonna label it here centered, and I'm gonna write it on the left hand side. Centered is -2, 0, 0. Hopefully that's clear. And so the vertices, let's take a look at the vertices, right? Well, one of the vertices, you have to move, I think 3 units in the x direction, right? So if you add 3, you get 1, 0, 0. If you subtract 3, you get -5, 0, 0. think hopefully you're okay with that. Just put it something like this. There you go. Yeah, so let me know if that makes sense, right? Hopefully, you guys agree why we moved 3 units in the x direction is because of the ninth underneath the first term there. That determines how far do we go from starting from the center. All right, so I think I want to see where this the origin is at. I think we can agree that the origin would be let me see, can I do that? I'll just move this out of the way. I think the origin will be somewhere here. So I will just do this. So this is my x-axis, something like this. And then the center, the origin is over there, the z-axis, and the y-axis is somewhere here like this. And then you should see the negative x-axis like this. This is negative x-axis. It would have continued up like that. I think maybe it's not perfect, but you get the idea. And if you want, you can put some rulings on it and make it look nicer, but I don't think it matters much. Like this, for example. There you go. And then I'll do the same thing here on the other side, just to give some contour, some direction. There you go, something like that. And then again, sometimes your sketch is questionable, and that's when I have to rely on your like whether you understand what type of quadric surface this is and other things. But again, it's okay. It's like hopefully that's clear. What else did they ask? They asked for label the vertices and the trace when x is equal to 3. So far we did everything except for the trace. Let's do the trace here. I'll do a small trace on the right side here at x equals 3. So how do we find the trace when x equals 3? You just replace the x with 3 in it, and we get the following equation. So we get 5 squared is 25. So 25 over 9 minus y squared minus z squared over 4 equals 1. So what I did here is that I replaced the x value with 3, right? Just replace the x value with 3 there into x. 3 plus 2 is 5. 5 squared is 25. 25 over 9. And then I guess I can subtract 25 over 9 on both sides. So we get negative y squared minus z squared over 4 equals 1 minus 25 over 9. Not so 1 is 9 over 9 minus 25 over 9. So that's 25 minus 9 is 16, I guess. So I get this. I get y squared plus z squared over 4 equals, I think it's 16 over 9. So how did I get that? Again, I just subtracted 9 minus 25, so it's negative 16, and then multiply everything by negative 1, and I got that. What kind of shape is this? This is simpler. This is an ellipsoid. I think you can multiply everything by 9 over 16th. So you get y squared divided by 16 over 9th. And then plus z squared divided by, what is that going to be? Let me see, 9. Yeah, I think it's like 64 over 9, like that, equals 1. So this is an ellipse. Yeah, there you go. So to clarify that, we'll get a ellipse in the YZ plane. So here is the y-axis and then the z-axis. And this is at x equals 3. So everything that we're doing here is a trace of x equals 3. And this is a plane that we have at x equals 3. So y, I'm looking at the denominator for the first term. So it's 16 over 9. The square root of that is 4 over 3. So 4 over 3, that's pretty much in the y direction. So we go negative 4 over 3, and then positive 4 over 3, like that. And in the z direction, then if we look at that, we have 8 over 3, because 64 over 9, the square root of that is 8 over 3. So it should be longer in the z direction. So it's 8 over 3 and negative 8 over 3. So we should see something like this there. Again, something like that. There we go. So again, in the z direction, it goes up to 8 over 3 and it goes as low as negative 8 over 3. But this is the trace that we get. It's an ellipse. That's pretty much what you're expected for this problem. Again, we could have rushed it. We could have done it faster, but I try to take my time so that it makes sense, like how we went from completing the squared, getting the standard equation. So this is the standard equation here. This is really, really important. Standard equation. Without that, I think you will lose points. And you can't just say that from here to here, get all of the information is impossible, right? So if you skip all of these steps and you just draw the perfect surface, that's questionable and you will lose points because this is missing right here. All right, questions? Questions about this problem? So it is a trace. So for number 55, right? Let me just look into that because I haven't seen it. So say you were looking at 55, right? Well, yeah, so here you set the y equals to 0 for this one, right? You see, you set here y equals 0 because the xz plane is y equals 0. So instead of giving you the equation y equals 0 or the value for y fixed at 0, I'm telling you to do it in the xz plane. So that or automatically tells you that the y value is 0 for that. Right? So we do the same thing that we did before, and for the trace, we just replace is that the equation that you get when you replace y with 0? I think you get something else, right? No, you get something else. You get like x squared um minus 6x minus z squared plus 9 equals 0. And when you complete the squared, I think you get it something circular, if I'm not mistaken, or no, maybe not circular, maybe it's a parabola. Yeah, something like that. Yeah, for that, if you get something like that, then you get z equals x minus 3 and z equals negative x plus 3 because there are two possibilities here. Remember, when you take the square root on both sides, you get plus and minus, right? So yeah, exactly, it's two lines. Correct. That's what it will look like. If I'm not mistaken here, yeah, so you get two lines intersecting. They form like an X shape, right? That's a trace that we get. And we can ask why that's the case, why we get that. I have a feeling that this will be like a cone or something, right? And that's why we get these X's, these X shapes. Yeah, right. Yeah, but that would be the trace for that, right? No, I think you have to, so to answer your question, Amber, right? So if you are asked to sketch something on the XY plane or the YZ plane, right? You have to sketch it with the shift, with the shift. So in our case right here, the one that we just did, everything was centered at the origin, but say we don't get everything centered at the origin, say we set, I don't know, y equals 0 or z equals 0, then we have to, you know, um, the center, it has to be at negative 2, 0 or something like that. So you have to take that into consideration as well. So if this was shifted, we will have to shift that as well. So, but it wasn't. It was centered at 0, 0 for that. All right. So I think let's answer another one. I think Mohammed had a question, right? You had number 4 in mind, right? We can go on to number 4 then. Let's see. Okay, there. For number 4, I think this is a question that is expected in every final exam. They're asking you to find the interval of convergence, including possible endpoints for the power series. And even if like if I were you, I will answer all the questions that had this idea in mind, like to find the radius of convergence and the interval of convergence, because it's going to be on the final exam, right? And it's going to be in our next exam as well. So how do we do this? So we apply the ratio test, right? So using the ratio test, ouch, let me see. Using the ratio test, we apply the following limit. So let L be equal to the limit as n tends to infinity of the absolute value of a sub n plus 1 over a sub n. So in our case, this will equal to the limit as n goes to infinity of the absolute value of, in parentheses, x plus 7th to the power of n plus 1 divided by 2 to the n plus 1 times the cube root of n plus 2, because we are going to have n plus 1 times the reciprocal of a sub n. So it's going to be 2 to the power of n times the cube root of, let me see, the cube root of n plus 1. All of this is divided by x plus 7 to the power of n, like that. So this is the limit that we are considering. Hopefully, we can take care of this x plus 7 to the power of n plus 1 and x plus 7 to the power of n. And then we can pull that outside of the limit. That's going to be the absolute value of x plus 7th. Hopefully, that's okay. We are also looking at this 2 to the power of n divided by 2 to the power of n plus 1. And hopefully, we can agree that that's going to be a 2 on the denominator for that. And then all of this times the limit as n tends to infinity of everything else that remains. That's the cube root. And again, hopefully you agree with me that this is just the cube root of n plus 1 over n plus 2, like that. Because the cube root of a divided by the cube root of b is the same thing as the cube root of a over b, right? What is this limit here? The limit for the cube root of n plus 1 over n plus 2. What is that limit equal to? Yeah, this should be 1, right? It is. If you don't agree with that, the cube root of this cube root can be placed outside by the rule of continuity. And so you end up taking the cube root of 1. So that's just 1. So we end up with this. We get L to be the absolute value of x plus 7 over 2. And by the ratio test, we want this to be less than 1 for the interval of convergence. Let me see, for the interval of convergence, we want L to be less than 1, right? This is what the ratio test tells us, that the series will converge as long as that limit is less than 1. So we have the absolute value of x plus 7 over 2 to be less than 1. And so we end up with this. We get the absolute value of x plus 7 is going to be less than 2. This number here at this moment, what is this 2 representing? This 2 represents the radius of convergence. Note, the radius of convergence, R is equal to 2. Sometimes they don't call it R, they call it rho. That's a fancy way. They use this other Greek symbol, letter, rho, for the radius of convergence. But again, our book uses capital R for the radius of convergence. I hope if that's not clear, you can find the interval of convergence and then you can figure out what the radius of convergence is. So in our case, that means that x plus 7 is less than 2, but is greater than negative 2, right? So what does that mean? Subtract 7 on both sides, we get negative 9th is less than x, which is less than negative 5. See, so we have to check the endpoints now. So we don't know if we include negative 9 or we include negative 5. So let's check. So at x equals negative 9th, what is that going to be? So we're looking at the original power series given all the way up there in the right corner. So this is just going to give us the power series from n equals 0 to infinity, but we're replacing x with -9. So we get this, we get -2 to the power of n divided by 2 to the power of n times on the denominator, the cube root of n plus 1. And this simplifies to the following. We get the sum from n equals 0 to infinity of -1 to the power of n divided by the cube root of n plus 1. So what can we say about this series? What tests are we applying for this series? Yep, there's only one test that we can apply. That's the alternating series test. I think that's obvious because it alternates. So by the alternating series test, it converges, right? It converges by the alternating series test. And it's easy to check that it's true that it converges because we can check the conditions. Number one, we have ace of n first of all. So ace of n is equal to 1 over the cube root of n plus 1. What was the first condition? I forgot. What was the first condition? There were three conditions, if I remember correctly, right? It has to be decreasing. That's one of them. Was it two conditions or three conditions? The limit has to equal to 0. I think there were two conditions, right? The limit as n goes to infinity of ace of n has to equal to 0. So there were two conditions in that. Yeah, so the decreasing part, sometimes we write it out like this, that ace of n plus 1 has to be less than ace of n. So it's the same condition as before, right? Yep. So there are two conditions. There we go. So in our case, the two conditions are met. And in the test, you don't have to state what these conditions are. You're saying that it converges by the AST. I will assume that that's okay. But if you say that it diverges or something like that, then you will be penalized because it's incorrect. And then here on the other end, we're going to have x equals -5. And I think if you did this several times, you will notice that they always end up being identical to one another. We end up with the sum starting at n equals 0 to infinity of 1 over the cube root of n plus 1. So one of them is the alternating series of the other. I think that's the case. You can tell that that's going to be the case all the time, right? So what about this series? Does it converge or diverge? What are we doing with this one? So I think we can do a limit comparison test. Yes, it will diverge. I think you can also do an
Can
integral
we use
test.
direct comparison, or can I directly compare with 1 over n or not?
Okay, direct comparison with
1 over n as the numbers get larger.
I think that's also a good idea. I think that's harder to spot, but I think it's like we have, I'm gonna start off like this, right? We have the cube root of n plus 1, and then I'll have let's see, nth like this. So the cube root of n plus 1 is an n. I think n is gonna be bigger, right? If you look at the graph for that, I will just put it here, like really. One of them is like the cube root of this, and the other one is n like this, something like that. You can imagine, right? The cube root and then nth. And you can do some examples like what if 64? Then the cube root of 64 is 4. So definitely. And then the reciprocals of this 1 over the cube root of n plus 1 and the reciprocal of 1 over n, they have the other inequality, the reverse inequality. So it will be like that. And therefore, what Michael was saying is that you can directly compare it with the sum from n equals 0 to infinity. But again, it doesn't matter where he starts. So I'm just going to assume that it doesn't matter where he starts, right? Because there can be some issues there. It doesn't matter where he starts. You can put 2, 3, 4, it doesn't matter. But 0, the other one is weird because you put in 0, plug in 0. So then this diverges, right? This is the diverges because it's the harmonic series or a p series with n equals 1. So this diverges by direct comparison. Diverges by direct comparison. Yeah. So again, the first test that came into my mind was the integral test, because I know how to integrate the 1 over the cube root of x plus 1, just because of that. It's the first thing that popped into my head. The second thing that popped into my head was what you guys were saying about the limit comparison test. And you compare it with the 1 over the cube root of n, and you use a p-series to determine that. Yeah, but all of that was good. So what is the interval of convergence then? So the interval of convergence, let's put IOC for interval of convergence. It will be everything from -9th, and we do include -9th, all the way to -5, but we do not include -5 like that. Again, the radius of convergence, the question didn't ask us for the radius of convergence, but if it did ask us to find the radius of convergence, we have it here. The radius of convergence is r equals 2. If you find the distance between -9 and -5, their distance is 4, and you divide that by 2. So you get 2 as the radius of convergence. It's always half of the distance between the endpoints of this interval of convergence. Okay, questions about this? Will this be in the test? Yes. Will this be in the final? Yes. It is important. Yes. Other questions? Anything else? Okay, so let's take a look at number 9, right? Number 9. Okay, there we go. So this is approximating the sum of an alternating series. So as you can tell, the series alternates. So we have to apply, I think the book called it an estimation theorem, right? For the alternating series. You can literally Google search that. It's called an estimation theorem for alternating series, exactly like that. So approximate the sum of the entire series with an error of less than 1 over 1,000. So I'm going to write it out as 1 over 1,000, like that. Okay, so I think we can start plugging in some values in it. For example, if we plug in n equals 0 into the series, we're going to get the first term, first non-zero term. So it's going to be 1 over, so remember n equals 0. So we get 1 to the power of 2, and then times 3 to the power of 0 plus 1. So 3 to the power of 1. That's the first term. This is not less than 1 over 1,000. So we have to continue. Minus 1 divided by, so we're plugging n equals 1 now. So we get 2 to the power of 2, and then 3 to the power of 1 plus 1 is 2, so 3 squared. I don't think this is less than 1 over 1,000, so we're going to continue on with another term. The next term will be obtained when n is equal to 0, 1, 2, n equals 2. So we get 1 divided by, so 2 plus 1 is 3, 3 squared, times, and then we have 3 to the power of 3. I think that's not enough. So let's plug in one more, 1 over 4, 1, 2, 3, 4 squared, times, and then 3 to the power of 4. I think this is not enough. 3 to the power of 4 is 81, and then 4 squared is 16. Is 16 times 81 more than 1,000? Will this work or no? It is? Okay, so maybe this works, right? So I'm looking at this expression, and I'm comparing that with 1 over 1,000. So note that 1 over 4 squared is 16th, and 3 to the power of 4 is 81, that this is going to be smaller than or less than 1 over 1,000, the desired error that we want. So therefore, this is going to be our answer. Our answer is this, and this is our justification on the right side here. Justification of why this boxed terms will be an estimate for the sum of the series, and that estimate will be less than 1 over 1,000, right? And the reason that we talked about this, or this works, the reason why this works is that all the terms that come after will not affect the decimal place, the first 3 decimal places. It will not affect it. It will affect maybe the 4th, 5th, or 6th decimal place, but it will not affect the previous decimal place, right? Yeah, so yeah, I will be posting the recording on Blackboard I think we posted the previous recordings as well. Yeah, so I'll post it on Blackboard as well. Yeah, so this problem is not a test problem directly because there will not be a question directly like this in the final or our exam, but part of a problem will, right? Part of it, you need this for a part of the problem. Yeah, so how will you calculate the exact value of the series, the exact sum? Is that your question? Like if you wanted to know the exact value, yeah, then that's a very tough question to ask. We wouldn't. Like they would not ask us to find the exact value for this series. We know that whatever these first three terms add up to will be less than 1/1000 of the actual value that the series converges to, which is really, really good to know. I think you don't have to write this out as a sum, because usually in the final exam, usually in the final exam, they will tell you to write out your answer as a sum of terms. And sometimes they say, write your answer as a sum of unsimplified fractions or something like that. Or write your answer as a sum of fractions, right? But I wouldn't, ask you to write it as a sum, yeah. Yeah, so you always want the terms to be less than 1/1000. I think from all the questions in the practice, none of them end up being exactly 1/1000. They will not. Yeah, but to answer your question, you want a strict inequality. So if it's exactly 1/1000, you don't want that. You want a strict inequality. So you will need that term to be included, right? Because this inequality here has to be strict. So if it's equal to it, then you will include that term as well, right? To answer your question, right? Yeah. Okay, yeah. So if it happens, that's my bad, right? But I don't think it happened. But if it doesn't, yeah, but we do include it. What do you mean by does it work the same for Maclaurin series? Is that your question? Yeah, it's exactly the same idea for Maclaurin series. Yeah. The Maclaurin series, it will lead you to an alternating series. So it will have the same idea like this, but it has to be an alternating series. Otherwise, it doesn't work. So the key here is that even if it's a Maclaurin series and it ends up being an alternating series, then it works perfectly. Yeah. So if you notice the Maclaurin series that we have, a lot of them have an alternating factor on them. In one way or another, especially in the final, right? Again, this is not a question that will be asked on its own. It will be part of a question that you need to know this more, right? So anyways, let's move on to another question, right? Okay, let's do number 17. I think you asked that before, so I'll listen to you now. So for number 17, yeah, I was thinking of a question similar to this one. We did talked about this in class, and we should know how to do it. Is it important for the final? This is not important for the final, but you should still know how to do it. Later on you will play around with series and you will end up doing something similar to what we did in class. So I'll do it here. So the idea here is that you want to end up with a Taylor series centered at x=2. So the centered for this one is not at 0, so it's not the usual one, it's centered at 2 instead. So we start playing around with f of x. I'll write this as 4 divided by 3 plus, and so I want this to be x minus 2 somewhere here. So first of all, I think I'll put a minus here, right? A minus and then negative x like this. You see it? And then I'll put another parenthesis here like this to put -2 here inside of that. So in reality, the denominator that we have here will be 3 plus x minus 2. So this is equal to 1 plus x. So again, we want it to be 3 plus x. So we add 2 here to this. So we add 2 to this. Hopefully that makes some sense why I do it. So we end up with f of x being written like this. We have 4 divided by 2 plus 3 is 5. 5 minus, in parentheses, negative, in parentheses, x minus 2. Like that. And why do we do that? So that the center for this is now at x equals 2. That's like a really nice trick to be able to manipulate that. This guy here will be 1. We want this to be 1 here, not 5. So we divide everything by 5. So that's my second trick. So I'll put 4 over 5 divided by 5 over 5, which is 1, minus, and in parentheses, negative parentheses x minus 2, and then divide this by 5 and close parentheses like that. So I'm trying to make this look like a divided by 1 minus r, like this, to have the geometric series form for that. So by using that geometric series, this will be the sum from n equals 0 to infinity of a, which is 4 over 5, and then r to the power of n, where r here is negative, in parentheses, x minus 2 divided by 5 to the power of n. So I'll just clean this out better. We have the sum from n equals 0 to infinity of 4 times negative 1 to the power of nth times x minus 2 to the power of nth divided by 5 to the power of n times 5. So 5 to the power of n plus 1. I just clean that out like that. Yeah, when you come to think about what we did, it's something really, really nice because we avoided a lot of steps. You could have done this the hard way by finding derivatives and then matching the terms and finding the values of each coefficient. And then you want to find the first non-zero terms. So now we can do it. If you plug in n equals 0, you start off with 4, and then x minus 2 to the power of 0 divided by 5, 4, 5. That's okay. The next term will be negative. When n equals 1, we get 4. And then we have x minus 2 to the power of 1 divided by 5 squared. And then plus, and then 4 times x minus 2 to the power of 2 divided by 5 cubed. And then the last one, the fourth non-zero term, will be minus, and then 4x minus 2 to the power of 3 divided by 5 to the power of 4, like that. And then this series would have continued, but the answer here will be the first 4 non-zero terms like this. These are, and they're all centered at 2 because as we said in class, what x value can be plugged in so that every term cancels out except for the constant term. That x value will be 2. So that way you know that the series is centered at 2, right? But the answer here will be those terms. Let me box them. This will be the terms. Oh, here. I didn't start at n equals 2. I started at n equals 0 because we know it starts at n equals 0 because the geometric series always start at 0, at least the one that we wrote in class, right? All right. Does that make sense the way we did it? Yep. Okay. Other questions? Let's see if yeah, let's do 27 then, right? 27 and then we can do 18. Here, find the area between the loops, right? That means that if you have a smaller loop and you have a larger loop, you want to find the area in between the little loop and the larger loop. So in between the loops. It's a weird way to ask the question, but it's a good question nevertheless. So we have to sketch this in the exam. A question like this to find the area between two polar curves, they will ask you to sketch, right? So let's make it a habit that for polar curves, we're expected to know how to sketch, right? Even though I didn't ask for this problem, I think you should sketch it. So is it clear why we're going to have symmetry about the x-axis? Is it clear? Okay. Yeah, so symmetry about the x-axis because we have cosine of theta there. So in our case, I think we don't have to make a table, but I'm always scared when you have an inner loop and you know you're going to have an inner loop because it tells you to. I think we're going to I'm going to do this right here. Oh, I don't even know what I'm gonna do. Yeah, so I'm gonna set this equal to 0. So think about this. If you set r, which is 2 minus 4 cosine theta, equal to 0, this will tell us when the little inner loop happens, right? So we have 4 cosine theta equals 2. That means cosine theta is equal to 1/2. That means theta is equal to pi over 3. That's one of the answers. The other one will be by symmetry at negative pi over 3, right? So I will do this because I know what I'm supposed to get. Again, if you want me to explain more, I was going to show you step by steps how to do it by graphing this on the r theta plane. When you have an inner loop, it's always best or a good idea to do that. But I'm assuming that you guys are already tried this. So this is the xy plane, not the theta r plane. So xy plane here. There we go. So we start when theta is equal to 0. Maybe I should draw some rays right here. This ray here will happen when theta is equal to 0. So what do we get when theta is equal to 0? When theta is equal to 0, we're just going to have 2 minus 4 and cosine of 0. Cosine of 0 is 1, so 2 minus 4 is negative 2. So we're supposed to go 2 units in that direction. So negative 2 units in that direction. So we work backwards. So we go 2 units in the opposite direction like this. So we end up starting here. That's where we start. So it's really weird that we start here. Next, what do we get when theta is equal to pi over 3? So pi over 3 is 60 degrees. So I will say 60 degrees is somewhere here. That's theta equals to pi over 3. How do we know it's pi over 3? Because I would have selected the next angle, which is pi over 2, but I know that r is equal to 0, and that the angle between 0 and pi over 2, that's what we got, pi over 3. What do we get when theta is equal to pi over 3? We get 0 for that. So it will go back to the origin. So we're supposed to move in this region. We're moving in the opposite region. So we're getting this little curve here. So I'll draw it out like this. We're getting this guy here. Why is it there on that specific side? Because we're supposed to be moving here. But remember, r was negative. So meaning that we are going to be moving in the opposite side. It starts here, we're supposed to be moving here. So we start here and we are supposed to connect this with the origin. So we're going to use this little arc, the one that we just drew there in green, that arc. Hopefully that answers a lot of the questions. Right? But anyway, so next, what is r when theta is equal to pi over 2? When theta is equal to pi over 2, so here we have pi over 2. Well, cosine of pi over 2 is 0, so we are going to get 2. So we go 2 units in that direction. So 1, 2, and we're going to get this little arc there. Now it's going to be here on this little piece of, there we go. And then we continue on. What do we get when let's see. Yeah, what do we get when theta is equal to pi? So theta is equal to pi. Now we are on this side right here. Theta is equal to pi. What is r in that case? Cosine of pi is -1. So we end up with 2 plus 4, which is 6. So we got to work with that. So 3, 4, 5, 6, -6. So we're supposed to be all the way there. So here, then here. Connect that. Because r is positive, we are staying in that specific quadrant. So I'm getting something like this. Be careful here. Yeah, there we go. So I'm getting something like this. I guess I could have worked this better. Ouch. There we go. Yeah, I gotta be happy with that. And I think you guys know the symmetry that we talked about, the symmetry about the x-axis, right? So basically, we're going to have this other loop like this, like that. And then we're going to have this other side like this. So we have 2 here. So 1, 2, -2. So we're going to have that because of symmetry. So we're going to end up with this here. Again, I took my time to do this, but I could have done it faster. So this is the shape that we end up with because of the symmetry that we talked about the x, ouch, about the x-axis. So we're going to end up with that. So the inner loop, to talk about the inner loop, I'm going to use symmetry for the inner loop, and you guys can tell me if you guys agree or not. Well, you don't have to use symmetry because we have this other angle. Let me see this angle here. Yeah, there we go. That angle. That will be negative pi over 3. Like that. So how do we find the area of the little inner loop here? Let's start off with that. How do we find the area of that inner loop? So area of inner loop. Say we are doing the integral. This will be the integral from where to where though? It'll be the integral from, yeah, see, we can do the integral from 0 to pi over 3. Yeah, so I'm going to put 2 times the integral from 0 to pi over 3. And then we're going to do 1/2 times r squared, where r here, r is going to be 2 minus 4 cosine theta squared d theta. Are you guys okay with that? Yep. Yeah, you can also do from negative pi over 3 to pi over 3, correct? But every time you have symmetry, I always encourage students to use symmetry because it saves you a little bit of time. Yeah. Okay. So that's the setup for the inner loop. And then what is going to be the area of the outer loop? Remember that the area of the outer loop, fortunately, when we do that, it will cover everything. Let me do it with this color here. It will cover everything. The outer loop will cover everything, including the inner loop, right? That's why this is a tough question because you gotta figure that out. So the area of the outer loop, area of outer loop, what is that going to equal to? So I'll use symmetry as well. Is the integral from pi over 3 to pi of 1/2 and then 2 minus 4, ouch, 2 minus 4 cosine theta squared d theta. Hopefully you guys agree with that, right? I'll pause here for a couple of seconds. By the way, the 1/2 and the 2 cancels out in every expression here, which is nice. And then to answer the final question, we will have to evaluate each of the expressions and then subtract the 2 of them, right? So the answer here will be the area of outer loop minus the area of the inner loop. There you go. Should have thought about that. Will it make a difference if we go from 0 to 2 pi? Yes, it will make a difference. Yeah, because this outer loop only starts at pi over 3, and it will continue all the way till you get to this other angle, which is negative pi over 3, but this would be let me see, 2 pi, so that's times 3, 6 minus 3, 6 minus 5 pi over 3, I think 5 pi over 3. So you can do the integral from pi over 3 to 5 pi over 3 if I'm doing this correctly, right? Like that. 5 pi. Yeah, I hope I did it right. Yeah, but you get the idea. It cannot be from 0 to 2 pi because this here is not, it's not part of it. Yeah. It will only be between these two angles like this. So that's why we only did this from 0 to pi, from pi over 3 to pi, and then double it like this. That'll give us this area here, and we doubled it. I see. Oh, my screen is lagging a little, so I'm just waiting for it to catch up. Yeah, so that's why we use symmetry, and we only used from pi over 3 to pi, and we'll get the area, but it will include the area of that little inner loop there. Yeah, so that's why we shouldn't do from 0 to 2 pi. right? Questions about that? Is it clear? Yeah, again, this is a very tough question because we only have one polar curve, and I guess this is as tough as a polar question can get, right? Because we talked about the area of a petal, right? We talked about the area between a polar curve and a circle, for example, and so on. But I think this one is tougher because you really have to think about like the setups, and then you have two setups, and then you have to evaluate each setup because they have different limits, so you can't combine them into single integral. No, I think for polar curves, I made up my mind. I will ask one question alone for polar curves. I will ask you to sketch polar curve and to find the area using polar curves. That I made up my mind. Yeah, so you will have to solve the each integral. If this was a question in a test, you will have to solve it. Remember, I'm only asking you for 5 questions in the test because I think that will be fair to do to ask you 5 questions. All right. Yeah, I think someone said for 26, and let me see, for 26, find the area of the inner loop of the curves. Yeah, so for this one, you only do one integral expression, right? For this one, you only one integral expression because it says the inner loop. So for example, if I ask for the area of the inner loop here, well, we just need the first expression here. We wouldn't need 2 of them, right? So that's the difference between that and that. How is it 1/2, not negative 1/2? Which one? Like when we solve for cosine theta. Yeah, when we solve for cosine theta here, I just added 4 cosine theta on the other side. So I get 2 equals, and then the 4 cosine theta should be on the right side because I moved the 4 cosine theta to the right side. All right, but again, I wrote it like this, but in my head, I moved this on the right side. Yeah. Yeah, and so you have to be really careful with these things. Like, so if you know that you messed up on certain things, you will be really careful with the final one. So, for example, in questions like this, if you cannot sketch it the way that we reasoned it out, then if I were you, I'll recommend you to sketch this in the r theta plane or theta r plane, and then transition that into this. But that's too much work. But again, that's to understand this better. And but again, the work that we did, look, is a beautiful curve. The angles are specified in our diagram. That there's an inner loop, and we know how large the inner loop is. This is not a circle, by the way. The loops that we get is not, they're not circles. So I remember this question. It was in calculus BC in high school, and I remember reading it, and I was curious to know what the answer of something like this would be. And then they say that the cow was fenced in the fence that looked like this, and it had a little pool to drink the water from, and then the pasture was outside of that, where the cow could eat, and so it was finding the area of the pasture the region there. It's like, I was like, how do you even do this? But anyway, so let's see. There was another question I missed. So for 26, would it be from 2 power 3 to 4 power 3? Since it is negative 1. Yeah, I think so. Yeah, so if it's negative 1/2 for that one, cosine is negative 1/2. I think you're right. It's going to be at 2 power 3. And so I'm not sure about the 4 power 3. It sounds correct though. I'll use symmetry there as well. I would use symmetry. I think for yeah, for that I will use symmetry there as well. So I think that will save us a little bit of time if we did it. But anyway, so someone had a question, right? Someone else had other questions. I don't want to miss it out. Number 18, yes. Ram. Number 18. Okay, there I go. Find the first 4 non-zero terms of the Maclaurin series. Let's see. This one is a tough question to ask, and you should know how to do this. is it likely for a question like this to be in the exam? I don't want to ask a question like this. I didn't think of putting something like that in the final. I haven't seen it, but if it is in the final or it's in the test, it will build up. It will build up from there, right? So let's try to see if we can do this. The idea with this, again, we'll try to build this up, right? So imagine I broke this up into parts. And part A, right? For part A, I'll ask you to let g of x be equal to, and this is out of nowhere, is 1 over x plus 2, like that. Or negative 1 over x plus 2. It doesn't matter what it is, right? So say this is our g of x. Can you write this as a power series? This would be the sum. Well, before writing it as a sum, you guys are okay for me writing this as 1 over 2 plus x, and for me to write this as 1 over 2 minus negative x, and for me to write this as 1 over, so 1/2 over, right? 1 minus negative x over 2. Are you guys okay with me doing that for this one? G of x. You might say, well, why is g of x? Okay, you will see it in the next part, right? So this will be the sum of the stars at n equals 0 to infinity of 1/2, and then here we're going to have negative x over 2 to the power of n. So g of x, which is 1 over x plus 2, remember that, equals negative 1, sorry, the sum from n equals 0 to infinity of negative 1 to the power of n divided by 2 to the power of n plus 1 times x to the power of n, like that. That's pretty much what this power series for g of x is. Okay, now for b, now this is trying to connect this with f of x. For b, find the power series for, let's put h of x. Again, it's weird, but it does the job anyways. Of sorry, find the power series for g prime of x. I don't want to make another function. Just put g prime of x. What is g prime of x equal to? What is the derivative of this guy here? The derivative of 1 over x plus 2 is, I think, negative 1 over x plus 2 squared. And now, you are seeing how this is transforming into f of x. You're seeing that in real time, how this is transforming into that. What is this equal to? This will be equal to the sum. I will write this wrong and someone will correct this, okay? I'll write this purposely wrong. So it'll be negative 1 to the power of n times x to the power of n minus 1 divided by 2 to the power of n plus 1. So something is wrong with what I wrote down on the screen here. Right? Yes, the series cannot start at 0. The series should start at 1. That's the mistake that I wrote out purposely. Hopefully there's no other purpose. Yeah, the derivative that we took was the derivative for this. That's the derivative for that is this guy right here. That's the only thing that we took. So we took the derivative from the left side to get that. We took the derivative on the right side to get this right here. And so that everything else is correct, right? And everything else is correct. Okay, now let's for part C, now we can answer the question. So f of x is equal to, right? Yeah, so everything else is correct. The only thing that was wrong was to start it at 0. So for f of x, we don't have a negative sign, we have x divided by x plus 2 to the power of 2. So do you agree with me that this will be equal to negative x times g prime of x? Right, negative x times g prime of x. So this would be the previous series that we had was for g prime right here. Can I do that? Can I do that? Yeah, there we go. This was g prime. All we have to do is multiply this expression by negative x. So lucky for us, we remembered our rules for this. Negative x, I think you saw this in Calc 1. You can introduce this inside the sum because it doesn't have any n into that. So we end up with this now, with that negative sign. We end up with the sum that starts from n equals 1 to infinity right? Yeah, so we don't have to change the exponent. If I think if I wanted the series, this series to start at 0, I could have shifted the indices and then it would have looked differently. Then I will put the n-1 here, or n+1. But if I wanted to start it at 0, but naturally it starts at 1, because when I take the derivative of a power series, I have to be careful with the exponents. The exponents for x right here, right? But after changing this, if I wanted to make the series start at 0, then I can do a shift of indices. So I could have written this so that it starts at 0, and then I could have changed this from -1 to the nth power to -1 to the power of n-1 or n+1. But in this case, I don't need to do that. It's an option for me to do it or not. So I find it convenient not to do it. And so here we have the sum from n=1 to infinity. And we have -1 to the power of n+1, because -1 times -1 to the power of n is -1 to the power of n+1, and then times n times x, and then to the power of n-1 times x is just x to the power of n, which I will write now. All of this divided by 2 to the power of n+1. So this is going to be our solution, our power series. They say to find the first 4 non-zero terms, but again, that goes without saying that we can plug in n=0. Sorry, n=1, not n=0. So if n is equal to 1, you're going to have 1 times x to the power of 1 divided by 2 to the power of 2, and then minus, and then you have 1 times 2 times x to the power of 2 divided by 2 to the power of 3, and then plus, I think you have 3, x to the power of 3, and then divided by 2 to the power of 4, minus 4x to the power of 4 divided by 2 to the power of 5. There we go. 1, 2, 3, 4, and then it stops there. These are the first 4 non-zero terms right here. If you wanted to find the first 4 non-zero terms. Yeah, and the series is a Maclaurin series because it's centered at 0, right? Yeah. Yeah, so the reason why it starts at 1, not 0, again, we wrote the rules in class, right? We said that when we take the derivative of a power series, and I can pinpoint that to the exact location in the textbook, but I think I made you guys copy that 2 times because I wanted you to remember that, right? So so when you take the derivative for it, if you notice, if you start at 0 and you replace n with 0, the power for x will be -1 here. And for that, that's an issue. We cannot have x to have negative powers. So it has to be whole, the powers for x have to be like whole numbers and positive. Right? So that's the reason why I cannot start at 0. Yeah, so how did I get that? Yeah, so the blue -x that I marked outside multiplied, this is -1 times x, right? So the -1 times -1 to the power of n, -1 times -1 to the power of n is -1 to the power of n+1. Just combined that. And then I combined the extra x that we have with x to the power of n+1. So x times x to the power of n+1 just gives me x to the power of n. Okay, got it. But that's how we answer this. Again, this is not going to be in the test because it does take a lot of manipulation to get to what you want. But you should be able to do this because these are skills that you will need later on to develop. These are very good skills to have. And in engineering, believe it or not, you would relearn a lot of these things. You're going to revisit a lot of the things that we already covered, especially in differential equations for engineering majors that go into differential equations. You learn a bunch of things, then you forget them, and then you take engineering, and then you come back to it and revisit it. And so same thing with calculus 3. You learn a lot from Calc 3 and you forget it, and you go back to you go into engineering class and you relearn that. So but these are skills that if you do it now, Even if you don't do it again for a while, eventually you will need them and it will come back to you, right? All right, any questions, any other questions, questions in general or anything else? Yeah, we can try number 13th, right? Let's see. So let's see. So number 13 is a perfect example of something that you are expected to know how to do on the final exam, right? You're expected to know how to do it. So I can either do number 13 or 14. So someone asked for 13 and someone asked for 14. So I have to do one or the other, right? Can't do both. Yeah, 13. Okay, I'll do 13. So 13th, 14th, and I think number 12 and number 11th, number 10th. These are all perfect examples of what you're expected to know how to do on the final exam. Number 15 and 16th, all of this. So I guess from 11, so no, from 10 to 16th are perfect examples of what you're going to be required to know how to do on the exam and the final exam, right? So let's do number 13 then. Here. There we go. So for number 13th, we have f of t to be equal to t to the third power times e to the negative t squared. So they asked for part A to find the first four non-zero terms of the Maclaurin series of f of t. So I'm going to write it out like this. So note this. Note, what is e to the x equal to? E to the x as a power series was a sum centered at 0, right? So it starts at n equals 0 to infinity. What was this inside of this right here? Yep, x to the nth divided by n factorial, right? X to the power of nth divided by n factorial. So in our case, we don't have that. We will need e to the negative t squared first. What is that equal to as a power series? It will be the sum that starts from n equals 0 to infinity. And in here, instead of x, we're going to replace that with negative t squared. So we're going to have negative t squared to the power of nth divided by n factorial. So it ends up being the sum that starts from n equals 0 to infinity of negative 1 to the power of n times t to the power of 2n divided by n factorial. Are you guys okay with that transition? Why do we need it? We're going to need it for this f of t. We just need to multiply everything by t to the third power, right? So f of t now, this is the answer for part A. F of t is equal to t to the third powered times e to the negative t squared. So I'll put this in a different color. T to the third powered times e to the negative t squared. So we have this equal to, maybe we need more space too. Okay, so we have t to the third powered times, and then we already have a power series representation for the rest, for this guy. E to the negative t squared, we already have that. Now it becomes clear why we did what we did before. And so what do we do with this guy? We introduce this in here, inside of the series. So we're going to get this to be the sum that starts from n equals 0 to infinity of negative 1 to the power of n times t to the power of 2n plus 3. And then all of this divided by n factorial. Questions about that? To answer the question here, find the first four non-zero terms. And that's the easy part. You just replace n with 0, 1, 2, 3, and that's it. You're done. So if n is equal to 0, you get t to the power of 3 divided by 0 factorial. 0 factorial is 1. If n is equal to 1, you get t to the power of 5 divided by 1 factorial. I think you get the idea. You get t to the power of 2, 3, 5, 7th divided by 2 factorial, and then minus t to the 9th divided by 3 factorial, and that's it. These are the first four non-zero terms for that. So if any of the terms was zeros, then we ignore it. We don't write it out. But it wasn't the case anyways. Questions about this? No questions? Okay. So for part B now, so use the results from part A to find the integral from 0 to 1/2 of f of t dt with an error less than or equal to 0.001. So 1/1000, right? Remember, this guy here is 1/1000. So we want the error to be less than 1/1000. So for part B, we're considering the integral from 0 to 1/2 of f of t dt. And we're going to do the integral from 0 to 1/2 of f of t. F of t was this guy here. There we go. And let me just put this around like that. There we go, dt. So how do we do the integral for this? We have the sum from n equals 0 to infinity of -1 to the power of nth divided by n factorial. And then I'm only focusing on finding the integral of this guy right here, only that guy, t to the power of 2n plus 3. Maybe I should just wait to catch up. So we're only finding the integral of t to the power of 2n plus 3. So the integral for that is t to the power of 2n plus 4 divided by 2n plus 4. That's pretty much what we get for that. And we, of course, have to evaluate all of this from t equals 0 to t equals 1/2. So we end up with this. We end up with the sum that starts from n equals 0 to infinity of -1 to the power of nth times 1/2 to the power of 2n plus 4 divided by n factorial times 2n plus 4. Of course, you can write it nicer once more. The sum from n equals 0 to infinity of -1 to the power of nth. All of these divided by n factorial times 2n plus 4, and then times 2 to the power of 2n plus 4. Something like that. Are you guys okay with that? How we get that the integral from 0 to 1/2 of f of t equals that? What do we do with this? Well, we managed to express this integral, this definite integral, as an alternating series, just like what we answered earlier on. How do you estimate the sum or the value of this alternating series with an error less than or equal to 0.001, or less than or equal to? So it's okay if the error is equal to that. Yeah, so for part B, you could integrate each term right here one at a time. I always like to do it this way. It seems more complicated than it actually is. It's easier than it actually looks. And for me, if you need more terms, you can always add n equals 0, n equals 1, equals 2, n equals 3, equals 4 really, really fast. So you can generate more terms than the one we see there. But yeah, you're right. You can just integrate these terms right here. And maybe you don't need all 4. Maybe you need 5. Maybe you need 6. Maybe you need more terms that there actually are from part A. But and also you need to know how to integrate power series, right, for later on. So it's a good practice. But anyway, so now we are going to start plugging in terms, plugging n equals 0. So n equals 0, that will just be 1 divided by 0 factorial is 1 times 4 times 2 to the power of 4. Okay, I think that's working. Minus the next term here will be 1 divided by 1 factorial, which is 1 times. So if n is equal to 1, you get 6 times 2 to the power of 6. And then plus, and you get 1 divided by 2 factorial, which is 2 times 8, I guess. And then times 2 to the power of 8. I I think that should do it, right? Because we get we compare this term, and you guys can tell me if this works or not. This guy, is this less than 1/1000? Yes, I think so, right? Because 2 times 8 is 16, and 2 to the 8th, well, 2 to the 8 is 2 to the 4th times 2 to the 4, there's 256 times 16. Yeah, definitely, right? So note that the answer is just this. This is answered for that problem, but our justification is that this term right here, let me write over here, justification, is that 1/2 times 8 times 2 to the 8th is less than 1/1000. Like that. Right. I guess the error could be less than or equal to. So they, in this case, the question said that it's allowed to be less than or equal to that, right? So it doesn't have to be strictly less than that. Right. Questions about this? So in this case, we didn't need all of the 4 terms from part A. We just needed 3 terms, and in reality, we also needed the first 2 because the third one is actually less than 1/1000 already. So this first 2. Yeah, so in the test, they will ask you to justify. I think in the final exam, they ask part C, and part C will be justify your answer from part B. So it's a justification, like why? Why is this 2 terms enough to guarantee an error less than a 1/1000? Is because the next term and the preceding terms will be less than 1/1000, and so on. So the series alternates right now, right? Yeah, so we plug in values until we get a term that is less than 1/1000. We take the terms before that, previous to that. So I highlighted this because this guy is less than 1/1000. So the first 2 terms are enough to guarantee that this first 2 terms is an estimate better than 1/1000, because the next terms will only affect the decimal place after the 3rd decimal place. It will not affect the 100th decimal place or the 10th decimal place. To say this guy is going to affect the, I don't know, the 4th decimal place or the 5th decimal place, so it's not going to change the value of this. It's like saying if you already have, I don't know, pi to be 3.1415, right? Say 3.1411, right? 1415. So that's, I don't know, like 4 decimal places already. So if you were to add like really, really small fractions, then it will not affect any of this. So say, for example, if you were to add 1/10,000, 1/50,000, then it wouldn't affect the estimate of pi anymore. You already have 3.14, for example. It wouldn't change that. Maybe it will affect the other decimal places after that, but not the 100 decimal place or the 1,000 decimal place, right? Yeah, so if every term ends up being less than from the very first, then you take the very first term. That's it. That the very first term already will be an estimate. If the first term that you tried, it's already less than the error that you want, then you just take the first term, and that will be the estimate of the series. But you need at least 1 term, right? Yeah. So even if the first term is less than 1/1000 in this case, then you still take the first term as the estimate. All right. So anyway, so we're gonna be calling it a day or night. All right. So we did have a like a productive session today. So the difference between part B of this question and question 14 is, let me see. The 14b is asking you for the derivative, not the integral. So this is the difference, right? So for 13b, we had to integrate. For 14b, you have to take the derivative, not the integral. So you do the opposite, right? But anyway, so I don't know how things. Yeah, the homework 3, as I said earlier today, perhaps you missed it, is that everything is now due until May 6th. Right? And if hopefully things go back to normal on May 6th. So then we'll have our exam on May 6th. But say worst comes to worst, and you know this situation is still going on, by May 6th, they will send us an email, and I will send you guys an email, which reminds me, I sent out an email like as soon as I knew that the class will be held online, and canceled the, or postponed, not canceled, but postponed the date of the third test. So I sent you guys an email, but I got some emails bounced back because they're not, there's something incorrect with your email. So you have to make sure you go on CUNY first and update your preferred email there. So I don't think it has to be CD mail email. It could be any personal email, but it has to be an updated email on CUNY first, so you can get the emails again. All right. So I think you had a question from before, Samir, right? So for the integral area questions, which degree? I didn't understand that when I read it first, right? Which degree did we start with? Like, are you referring to the polar area between polar curves? Yeah, but what do you mean by degree though? So if we go back to that polar question right here, um, how did I get the area? Like, you mean this area or that area? The inner loop, the outer loop? The inner loop. So, well, the inner loop here is bounded between pi root 3, well, negative pi root 3 and pi root 3 here. So in class, I think we did as I said today, if I wanted to understand this better as a student, I will sketch the curve. This r equals 2 minus 4 cosine theta. I will sketch that on the r theta plane. So I'll literally create, we did this in class like 3 times or 2 times at least, where we had the theta axis and the r axis here. And you did this in pre-calculus. And I will sketch this here. And then say, you know, I think it will look something like this. I'm just guessing here because I like guessing, I guess. It will look like this right here. Like that. Maybe not like that. So it starts at that -2, it will go to 0, then it will go down like this. It will look like this. I don't know. Maybe it will look like that, right? So at pi, which is this guy here, at pi will be 6, and then here is 2 pi somewhere here. It's 2 pi. So I think yeah, I'm expecting it to look something like this. Maybe I'm wrong about it. So let's see. Power 0 to, yeah. So here we have the inner loop. The inner loop in this case will be this. You will continue this curve on the left side, and the left side you will continue the curve like this here. So because it's symmetric about the x-axis, so ouch, like this. These are some suggestions that, but the inner loop that we kind of highlighted there is this inner loop here. This is the inner loop there, and it will go from this angle to that angle right here. So that's why the inner loop will go from negative pi root 3 to pi root 3, but I use symmetry. So I just find this guy right here from 0 to pi root 3 for the little inner loop there. So that's why I only use a half of that. So the 2 here that is outside is because of the symmetry that we have there. But again, the inner loop is this guy here. We did like 2 examples or 3 examples. Yeah, so if I were you, I will just like you go to YouTube and say find area of inner loop polar curve, something like that, and you have some examples there. But again, I will recommend to sketch this in the theta R plane, but it will take more time, but at least you will understand this more in depth and say like, okay, you see it from a different angle, I guess. Yeah, you guys should have received an email from John C. David about the Artino lab, right? It is available like 7 days a week. It is available every day of the week. And so you should take advantage of that. Yeah. And so if you have any questions, I think you can email David Sijan for that, right? All right, but anyway, so I'm gonna stay here for a couple of more minutes, but I'm gonna stop recording the session, right? Yeah, and anyone can sign up, anyone, literally. All right, but anyways, I'll see you guys. Have a good night. I will stay here for a couple of more minutes in case you guys have any questions or anything like that. But other than that, I'll see you guys on Monday, hopefully.